Hello everyone and welcome back to the Cisco Optics Podcast, where we talk about pluggable optics for networks. Lasers have been around for over 6 decades. Since their invention, they have found their way into many applications that have changed our lives. Optical communications is of course one of them, and there are many that may surprise you. There's also still plenty of room to take laser performance to new heights, leading to even more new applications. This is episode 35, and we begin a new conversation with laser and optics expert Juliet Gopinath, professor at the University of Colorado Boulder. We begin with her work at Lincoln Laboratories on improving laser performance. Juliet Gopinath is the Alfred T. and Betty E. Look Professor of Electrical, Computer, and Energy Engineering and Physics at the University of Colorado Boulder. She received her BS degree in electrical engineering from the University of Minnesota and her MS and PhD degrees at MIT. She was a member of the technical staff at MIT Lincoln Laboratory from 2005 to 2009. Since then, she has led a research group at the University of Colorado Boulder. Her current research interests include ultrafast lasers, nonlinear optics, mid-infrared materials, spectroscopy, orbital angular momentum, and adaptive optical devices. She has published 78 peer-reviewed journal articles and over 97 conference presentations. She is a recipient of an R&D 100 award in 2012 and is an Optica Fellow. She served as an associate editor for the IEEE Photonics Society Journal from 2011 to 2017, the associate director for Qubit in 2019, and is currently an associate editor for Optica. Juliet also teaches a free online course on active optical devices. Just go to coursera.org and search on active optical devices or search on Juliet Gopinath. If you haven't already, please subscribe to this podcast. On Apple Podcast, you would click the follow button at the top now. We're part of the Cisco Podcast Network. Check out our blog at blogs.cisco.com and search on hashtag Cisco Optics Blog, all one word, no hyphen, and no spaces. You'll find podcast notes and links there too. For our YouTube playlist, go to youtube.com and search on Cisco Optics. And for product information, go to cisco.com/go/optics. And now join me as I talk with Juliet Gopinath. Hey Juliet, how are you doing?
I'm doing well. How are you?
Good, thanks. It's really nice to reconnect with you after not just years, but like literally decades, right?
I think it's been 2 decades.
How did grad school end for you, and what did you do after that?
Yes, so it's been a long time. I finished my PhD in 2005. In early 2005, and then I joined MIT Lincoln Lab, and I worked there for 4.5 years. And then I was lucky enough to get a faculty position at the University of Colorado Boulder, and so I've been here since 2009.
I would say it's not just luck. I think there's usually more than luck involved in something like that.
I think there's a lot of luck in winning faculty positions. It also clearly takes some skill, but there were some nice circumstances that came together.
That's great. So, can I ask what group were you in at Lincoln Labs when you were there?
So I worked in I think it was the quantum electronics group. The name has changed, and it's now the Laser Technology and Applications Group. And I believe It was founded in 1990. It was founded in 1976.
And for people who aren't familiar with the terminology, what does quantum electronics refer to? And the new name, lasers, what was it again? Laser
Technology and Applications.
Technology, okay. So what is quantum electronics, and then what does laser technology encompass?
So quantum electronics was a fancy name to refer to essentially laser technology. And so the new name reflects in a more relatable manner the group's activities. So the group works on all kinds of different lasers and laser applications, including semiconductor lasers and solid state lasers. And these go into the real world in a variety of formats.
Can you give some examples of these formats and real-world applications?
So when I was at Lincoln Lab, we worked on what are called slab-coupled optical waveguide lasers. And this was a new way that you could make a high-power semiconductor laser with a low confinement factor. What that meant was that we could get high pulse energy and also high powers with a large mode area so that it could be coupled to fiber with high efficiency. Since I left, there's been a lot of really nice work in terms of making narrow line width lasers, semiconductor lasers. So you can imagine these can be used for all kinds of applications, ranging from frequency conversion to applications that require pulsed systems. The group at MIT Lincoln Lab is also really well known for its development of the cryo-ytterbium YAG solid-state laser. And so essentially by cooling the laser crystal down to cryogenic temperatures, the thermo-optic coefficients all scale in the right way. And so you can make a very high power laser with good beam quality because you can actually manage the thermal load. And that really, the demonstration and pioneering of that laser system, the credit needs to be given to T.Y. Fan, who was one of the group leaders of the group. I remember him.
So, okay. I think your explanation was a bit of a mouthful for people who aren't familiar with lasers. Let's kind of work our way backwards a little bit. So you mentioned, in short, cooling the material down makes it a lot easier, I think, basically to crank out lots of power with a nice beam quality. Is that the point of the cryogenic application?
Yes. So if you want to make a high power laser, the name of the game is that you really need to be able to remove the heat. And so and as a material heats up, things will happen like it will thermally expand and the index of refraction will change. And all of these things are very undesirable. And in order to be able to extract the heat, you also need to have good thermal conductivity. And so by cooling the material down, we were able to get all of these properties to scale in the right direction so that we could extract the heat. And by good beam quality, I mean a nice, well-behaved Gaussian beam coming out from the laser. And that is really critical if you want to use this for applications.
Okay, so Gaussian beam meaning there's a nice peak at the center. There's no like spots. Like if you shine it against a wall and you look at it on a camera, if it's not visible, you don't see like local spots in the larger spot, right?
That's correct. If you have an ill-behaved laser beam, often you will have hot spots or you will have power at the edges. And then if you then say focus it down or do something with it, these things can seed damage in components further downstream.
Okay. And you mentioned in applications, frequency conversion was one of the applications. Can you explain what that is?
Yes. So sometimes we can't get the color of laser that we want. There is actually what's called the blue-green valley of death. And so it can be very, very hard to make lasers.
I haven't heard that called the Valley of Death ever. I missed that somehow in grad school.
Oh, really? So if you want to be able to propagate light through the ocean, you really need a blue-green laser. And it's a problem that has sort of been going around the washing machine for a long time. It's very, very difficult to make a laser there. And so what people often do for hard to reach wavelengths is they essentially use nonlinear optics to convert the color of the light coming out to another color. And so what that means is that we actually need to start with something which has high peak power or pulses, so that we can no longer have a linear response of the medium, but we have a nonlinear response.
I don't know if our listeners realize what a huge deal this is, because I don't know if people think about. In my opinion, it's almost like magic that you can start with one color of light, have it go through some kind of material, and it comes out a different color. To me, when I first saw that, I'm like, that is just like I said, it seems like almost magic. And I don't know if people realize, I have a feeling people take for granted the fact that we have all these lasers and they can do all sorts of things. I don't know if people realize what a funky thing this is. So keep me honest here, because it's been a while since I've been doing this. The nonlinearity is basically a result of the light intensity being so strong that when it goes through the material, the index of refraction is no longer just an index of refraction. It gets affected by that intensity of the light. So the light's basically just knocking around the molecules or the atoms. And it does all these weird things and it generates these different colors. I mean, is that still accurate, but in like lay terms?
I would say in general, I guess the way I would look at it is that when light interacts with a medium, it essentially excites the electrons and it excites them in a harmonic oscillator fashion. And those electrons then re-radiate the incident light. But if one turns up the power, we now get a nonlinear response that deviates from that harmonic oscillator. So essentially, we're exciting a nonlinear polarization response. So you're essentially driving things out of the linear regime. And once you do that, if you go through the math, you will see that there are different frequency components that appear. I think this phenomena, of being able to generate new frequencies with high powers, basically going out of the linear regime, I think it's not just confined to optics. That happens to be the use case that I'm most familiar with. And I would also like your listeners to know that if you want probably one of the most commonplace examples of nonlinear optics, pick up your green laser pointer. Your green laser pointer is powered by 1,000 nanometer laser. So that's basically beyond the wavelength you can see. You can see between 400 to 700 nanometers. And then we have a special crystal that uses the nonlinear optics that I've described to upconvert to around 500 nanometers in the green.
So it's basically exactly half of that 1,000 nanometer wavelength.
Yes.
Yeah, that's a really good point. And I do remember when those green laser pointers first came out, I was just floored that you had that nonlinear conversion in such a tiny little compact package. So, okay. So we're still kind of at Lincoln Lab stage. That was the first part of my new conversation with Juliet Gopinath. Next time, we'll get into time-resolved spectroscopy. Juliet also teaches a free online course on active optical devices. Just go to Coursera.org and search on Active Optical Devices or search on Juliet Gopinath. Subscribe to this podcast, and we'd really appreciate you helping to get the word out. Share this with friends and colleagues that come to mind when you think of network technology and optics. And leave a review on Apple Podcasts. We're also on all the other major podcast platforms. You may see the Cisco Podcast Network come up when you search for Cisco Optics Podcast. That's where we live, and you can find other great podcasts there too. Also, check out the Cisco Optics blogs at blogs.cisco.com and search on hashtag Cisco Optics blog, no spaces and no hyphens. We also have educational videos on YouTube. Just go to youtube.com and search on Cisco Optics. Thank you for listening. This is Pat Chow, Product Manager at Cisco Optics. The next episode is part 2 of my conversation with Juliet Gopinath. Until next time.